So for this one, we are given f of xy equals just x alone, okay? And our bounds for x are 0 to 1, and our bounds for y are the following: 1 to e to the x squared. Okay, so these bounds constitute our domain. All right, they let us know information about D. Okay, so we basically have all the information. We have our bounds and our f of x, y. So we can set it up. So we'll do the constants on the outside, right? So 0 to 1. And then we have our more complicated bounds, which are 1 to e to the x squared. And then our f of x, y is just x. And then we have to figure out, so for the inner bounds, we have, is this x or dx or dy? And this will be a dy, right? Because these bounds corresponded to y. So we have to have the y stuff on the inside. And on the outside is then x stuff. So that would be a dx at the end. So let's start solving this here. So we have from 0 to 1. And then we're treating x as a constant first, right? Because we are integrating with respect to y. So there's just an x here, and then that's a constant, and this is y because we didn't have one before. And then as y goes from 1 to e to the x squared, all right? And then our dx, of course. Okay, so then when we plug these in, we get x times the following: e to the x squared minus 1. Okay, so then when we distribute the x, we just get x times e to the x squared minus x times dx. Okay, and at this point I'm going to just split it up into 2, so it's a little bit more simple. So x times e to the x squared minus, dx, can't forget the dx, minus, and then the same thing here. You can always break it up if you want. Pretty much whatever floats your boat kind of thing. Okay, so we're at this point, and this second integral is pretty easy, so we can just copy it down and solve it later. And then this one, though, this requires a u substitution, so then I'll draw a little arrow here. So we want to make our u be x squared. That's what I would recommend. And then du is then 2x dx, and I like to get dx by itself, so we can just sub it in right here. So then dx, getting that by itself, is du divided by 2. Okay, so the way I'll rewrite it on the next page in terms of u. All right. Okay, so if we were to rewrite the first one in terms of u, we would get nothing can replace the x in front, so that just stays there. And then we have e to the x squared, which is now u, e to the u. And then dx is replaced by du over 2x. Oops. Okay, hold on. Going back. All right. Okay, sorry. So on the last page, I said that u is x squared, right? And du is 2x dx. I don't know if I wrote the x in. Sorry. There is an x here, 2x dx. So when you solve for dx, you get du over 2x. Yeah, this x is important. Sorry, on the last one I know I didn't, I only had a 2 on the bottom. But there is an x. Yeah, if you're confused, I'm sorry. But, okay, so we got that all sorted out. So then this is what you would plug in for your dx spot. Okay. All right, moving on. So, as you can see here, the x on the bottom is pretty important because it does cancel out with the 1 on the top. Okay, so now we're just left with things in terms of u, which is good. So then we have 1/2 e to the u du, which is pretty simple to integrate. So we're going to get 1/2 e to the u. All right. And here, like I said, I'm just doing the first part. And then we also have our minus 0 to 1 of x dx. So now at this point, I'm going to replace the u with x squared and reinstitute the bounds for x. Okay, so what we're going to, excuse me, what we're going to get is 1/2 e to the x squared, and as x goes from 0 to 1. And then here, let's work on the second part too. We have 1/2 x squared as x goes from 0 to 1 as well. Okay? So at this point, we're just going to plug things in and solve for the rest. So we'll get a 1/2 times e to the 1 squared minus e to the 0 squared. And then minus a 1/2 times 1 squared minus 0 squared. And this is a 1/2 times e minus, and this turns into 1. Okay, so e minus 1. And then we have a minus 1/2 times 1 here. And then the 0 is just right there. Okay, so then we end up getting 1/2 e minus 1/2 minus another 1/2. So this turns out to be e over 2 minus a whole 1. Okay, so yeah, that does it for that question. Sorry about the little mix-up over here, but yeah, so other than that, it's pretty simple, or maybe not even simple, but once you get some more practice and do some more problems, you'll get in the hang of it and doing the process over and over again and getting good at seeing what works when. Okay, now for the last problem. So let's say we're given 0 to 1 and y to 1 of sine x over x and then dx dy. Okay, so first of all, let's try integrating. So let's do the inner one. So we are integrating with respect to x, which we see two functions of x, basically, one on top of the other. So this is going to be some kind of combination of, I don't know, I mean, seeing this here, I would think like integration by parts, which is not the prettiest method to go. It's actually kind of ugly at times. So what I'm going to do here is actually look for a kind of a shortcut, basically. And as you'll find, a lot of things in math are shortcuts. Like theorems are really big tools to do shortcuts. But anyways, so we're going to look for a little bit of a shortcut. And in this way, I'm going to, yeah, I won't give it away yet. But let's try graphing our domain. So in this case, domain, remember it's determined by the bounds on x and y. So this part here, this f of xy, that doesn't really matter in as far as the domain goes. It's not directly connected to it other than it's being integrated over that domain. So anyways, so let's look at our domain. So these parts are important, the bounds. So let's graph it. So we have our x and our y, and we see that x, so 1 and y. Okay, wait, let me rewrite that. The bounds for x are the inner ones, right? So it goes from y to 1. Okay, so this is how you kind of transform it into these inequalities. And y, which are the outer ones, go from 0 to 1. Okay, so x is going from y to 1. So 1 is the upper bound here. So that goes, it's a vertical line for x. And x equals y is this line here. That's actually pretty good. So this is x equals y, right? So it goes from y, so this curve here, to 1. So it's like going from here to here, right? So this is a horizontally simple. That's what they're considering it. And then we see that y goes from 0 to 1, which it does, right? Because these two intersect at 1. Okay. So anyway, so this is our domain. That's what it looks like graphically. So let's see if we can do any shortcuts here. So the way they have it set up is x is in between two functions of y. So that implies that this is, they're considering it horizontally simple, right? And we can see that in the picture because I drew lines from one curve to another. and they turned out to be horizontal. So this is horizontally simple. And the shortcut here that we're going to use, or the one that I'm going to use, is transforming this, or not even transforming it because it already is, but using the property of this domain that it is vertically simple as well. So if I were to go from one curve to another, I could also draw straight lines up and down, so vertically. So let's turn it into a vertically simple domain, and maybe that'll be an easier way to go. So if we do that, then we get, so we have to get y in between two functions of x, and x in between two constants, or two numbers. So automatically we see that x it stays in between 0 and 1, right? So 0 and 1, so that's good. And y stays in between the line down here, which is y equals 0, that's the x-axis. So that's its lower bound. And its upper bound is when it hits the line, right? And this line is y equals x, okay? So y equals x is the upper bound for this domain. Okay, so now we have these new bounds. So this is taking it to be vertically simple. All right, so now let's rewrite it in these terms. Okay, I will do so on the next slide. Okay, so we're going to keep the constants on the outside, so 0 to 1. And then this time we have going from 0 to x, and these are our y bounds. And then as I said before, the f of xy is pretty much unaffected by everything that we're doing with the domain. Because we're kind of, I guess you can consider it like rephrasing the domain, or just putting it in different terms. Okay, so on the inner, this is our dy, and on the outer, that's our dx. Okay, so what we did here essentially is the changing, what was it called? The changing of variables, or changing the order of integration. That was it. Changing the order of integration. All right, so that's what we did because we switched the place of the dy and the dx. Okay, all right, so now let's try this and see if it comes out a little bit nicer than the other method. So if we just look at the inside, this is good because we're integrating with respect to y, so that means we're treating x's as constants. So this whole thing here, that's just like a number. That's just sitting there. So that'll be sine x over x. And then if we integrate with respect to y, we'll get this constant times y. And y goes from 0 to x. Okay, so here you'll see how this works out. So we have 0 to 1, and then we have sine x over x, and then we have x minus 0, which is great because this x on the top here, because 0 goes away, and the x on the top cancels with the 1 on the bottom, making this problem a whole lot simpler than it was before. So this is what we're left with, from 0 to 1 of sine x dx, okay? So now, at this point, we just integrate like normal, so we'll get negative cosine x as x goes from 0 to 1, okay? And then when we plug them in, we get cosine 1 minus a negative cosine 0, which is equal to, this turns into positives, and cosine of 0 is just 1, so 1 minus cosine 1. Okay, and that's our answer. That's as far as you can go without a calculator, because I don't know cosine of 1 off the top of my head, and I'm pretty sure most people don't. But if you do, then congratulations. But anyways, so yeah, that's our final answer for that problem. Okay, so I hope that helped. And again, good luck on your homework, and I'll talk to you in the next video.